Anyhow, here we go. Excuse me, class has begun. Thank you. This is being recorded, so I have to sound like I'm on top of things. Yeah, they do. So yesterday, you did this question. We figured out, we came up with this drawing here. So, as we talked at the time when t is equal to 0, what would you guess the velocity is? Zero velocity? How would we know for sure? We would plug it into our velocity function, which we have here, and it would actually be 60. So it's actually moving at that point in time. And so yesterday, particularly in the afternoon, but maybe a little bit in the morning, a number of people were kind of arguing, well, time doesn't exist. Like nothing's happening before t equals 0. To which I replied, you mean there was nothing before you were born? Like for t equals 0 in your life, that's when everything began in the universe? I think not. So just because we're calling some point in time t equals 0, that doesn't mean nothing was happening before that. So in fact, in order for it to be moving at 60 meters per second at t equals 0, it had to be moving at t equals -1 or negative something. Shh, gentlemen. So something was happening which brought it to this instant in time when it's moving at 60 meters per second to the right. And so it's moving to the right, and what's happening? Speeding up, slowing down? Slowing down, so it stops. Put your hand down so you can think with me. So it stops when t equals 2, and then does it speed up? It speeds up and then slows down again so it can stop again. And what did we say about acceleration and velocity related to speeding up, slowing down? If they're opposite directions, what's happening? It's slowing down. If they're in the same direction, speeding up. Now, with that information, let's look at this graph and think about the red parabola, that's velocity. The green line, that's acceleration. How do we know when they're in the same direction? Velocity and acceleration. How do we tell direction when we have a point moving on a line? Yep. Negative and positive. So as we look at our x-axis, if one function is above the x-axis, the other is below, our object was slowing down. Because here between 0 and 2 seconds, my velocity was positive, my acceleration was negative, opposite directions, so my object, whatever it was slowing down. But then between 2 and 5, 2, 3, 4, 5, yep, no, 2 and 4 seconds, no, 2 and 3 seconds, the red graph, green graph are both on the negative side, so they're both in the same direction, so my object is actually speeding up. When the acceleration hits 0, that's when it switches direction. So that's at the time of 3.5 seconds, I guess I should have said. And then they're in opposite directions up till 5, so it's slowing down up till 5. Then they're both positive after 5, which means it's going to start speeding up again. So same information, but just represented in a different way, and we can figure out where it's speeding up, slowing down. If we go back to our blue graph, the cubic there, and we think of the slope, as I go from left to right, at a time of 0, I have this positive slope, but it decreases to 0 at 2 seconds. So did it speed up or slow down? It slowed down. And then it goes negative, but in terms of speed, it'll be speeding up because we're increasing the size of the slope. Not the number, because it's negative, but the size of the slope is increasing until we reach some point here. And what happens to our point there is all the way up to 3.5 seconds, my graph is curving down. And that's because my acceleration is negative. But then where it switches to positive, my graph starts curving up. So what we will be exploring more in chapter 5, for a little bit, is when my acceleration is 0, when my second derivative is 0, my initial function actually has a change in how it curves. We call that an inflection point. So it's concave down up until 3.5 seconds, and then we'd say it's concave up after 3.5 seconds. So we can see there's a relationship between our original function and our second derivative, not just the original function and the first derivative. Okay, Yami, you had a question a while ago. Well, I printed one for everybody. I don't know if I have any extra. Your note package. Nobody else comes looking for one. Welcome. Yes. Yep. Yeah, wherever we want to know an instantaneous velocity, we can look at our velocity function here and plug in whatever time we're interested in. Oh, sorry, I guess that's the... That answer your question? Say it once more. This one down here. What needs to be perfect for sketching graphs like this is, and I'll highlight things so if anybody attempts to watch this video, is going to be this, where my original function has a maximum and its derivative has a 0. Or here, where my original function has a minimum, it's slightly off, so I should fix that, and my derivative has a 0. Or here, my first derivative has a minimum, and my second derivative has a 0. So where I put those dotted lines, those will be the key points. And now we also know that at this point, the shape of the curve will switch. That will make a bigger deal of in chapter 5. Yeah, when the acceleration was 0, that'll be a minimum or a maximum. It just means the first derivative function, in this case velocity, had a horizontal tangent line at that point. Yes. Yes. Make sure you sign out. Yeah, because for acceleration, we have the equation, I guess we just figured it out here, of 12t minus 42. Yep. So we can find the 0. That's the key point. We want to make sure where it is. The slope we're approximating. Question 16. Sorry, go ahead. If it's too much off. So if a little bit by your standard is too much by my standard, then yes, I will take off marks. Oh, back to 16 again. Okay. So for the next section, there's a warm-up question. So take a look at that question, see what you can come up with, and then we'll look at it in a moment. So here's what's happening in this question. We have grain pouring into a conical pile, which reminds me of a story, which I don't need to record for the video, so I'm going to pause this again. Ha! To you online. Back to the question. What we're told about is that the height is equal to the base radius. And this just depends kind of on the The friction in whatever, in this case it's grain, whatever it is that's pouring out. If it's really smooth, it'll spread out wider. If it's has more friction on it, it'll be more of a steep pile. To make things simpler for us, we're saying that the height is equal to the radius, which is important because if I'm going to take the derivative of this, I'm looking at how does my volume change as my radius changes. But the height is also changing. So if I have 3 or more things changing, then I would have to actually use a product rule to take this derivative. But that's more complex than we want to get yet. We'll get there in a couple days. So if I know that height is equal to the base radius, I can rewrite my volume equation as a function of radius as 1/3 pi r cubed, because my h is equal to r. Then I can do the derivative with respect to r. So because I have v as a function of r, I'm not going to use the dv dr version, but that's what I'm doing. So v prime of r would equal pi r squared. Interesting. It is a circle. That's the area of a circle. So somehow there's a connection between how the volume of a pyramid changes that's connected to the area of the base. Oh, why is that? Imagine you have a cone and its volume is growing. So let's make it a little bit simpler, as in instead of having the cone in that direction, imagine we have a cone in this direction, like that. Suppose it's one of those useless little paper cups, and you're pouring water into it. As the volume changes, where does water get added? It gets added to this top surface. So imagine you get such a thin layer on top that essentially the thickness is 0. The volume that's added is equal to the area of the circle at an instant in time. Because at an instant, there's no thickness to it, but it's covering the whole area. And so that's the connection between the rate of change in volume and this area of the circle, which is the base of our cone. So we have that. We want to know when the base radius is 5, so we just plug the 5 in. How I did the derivative? So sometimes we simplify these down, sometimes we don't. I'll get to your question in a moment. In this case, we'll go with the exact value, 25 pi, which is about 75, 78, in that range. We're given a radius in meters, and that means our volume would be cubic meters. So this would be meters cubed per meter. Can I reduce the meters? No. Because remember, this is a rate of change. A rate is a comparison between two things that have different units. So I'm comparing a volume, meters cubed, to a radius, which is just meters. I don't want to reduce it because it loses its meaning. Yes? I take the derivative because I want to know the rate of change in volume, which is my y value, with respect to the base radius, which is my x value, at the instant, so it's an instantaneous rate of change, for which we need a derivative. Volume is changing as the radius changes. So you imagine that grain is poured into the pile, it kind of flows down, it kind of adds to the surface of this, but it flows right down to the bottom, so the bottom is getting wider. So as that bottom of our cone gets wider, how does the overall volume change? That's what we're looking at. Nope. it's solid. Like it's full, everything we can see at the moment is full of grain, and as grain is piled on, it goes on to the top here, but then that kind of flows down the side and ends up making the base get wider. So the more grain that comes, the bigger our cone gets on the bottom, and also the taller it gets, right? And we said the radius and the height will always be the same. Back to the derivative. I had 1/3 pi r cubed. We just bring the 3 down in front, times 1/3 is 1. Subtract 1 from the exponent, there we go. So since it was the derivative with respect to radius, we're treating it like an x value where I don't have to do a chain rule by multiplying by dr d something at the end. Yes, Elliot? Yep. That's right. And the radius get bigger. Yep. Yep. Yes. Then we would have to use a product rule and a chain rule. And that's what we'll do with related rates. So this question isn't really realistic as it is, because, well, it sort of is, but usually we're not interested in how the volume changes with respect to radius. More often we're interested in how does the volume change with respect to time, right? So how fast is it growing? But we'll come to that. Okay, let us move on to a physics application, different than velocity, acceleration, speed, position. There we go. So we're just picking one application here. There are all kinds of things we could do, but this is the one your textbook makes use of. So we're going to look at this one too. Imagine you have a rod or a piece of wire and if whatever this wire is made up of has uniform density. So suppose you have a piece of copper wire. Probably the density is fairly uniform all the way through for it to be useful in the wiring in your house. Situation we'd say it's homogeneous if that density is uniform all the way through. What we're going to look at is a situation where it's not homogeneous. In other words, the density in our rod changes at different points in kind of as we go along the length of it. Okay? Which in reality is a little more realistic because it would have to be ultra pure for it to have that constant density. And the more impurities it has in it, the more the density is going to change at different points along the way in our rod. All right. So our density is represented with this Greek letter rho. Have you used that in physics? Anybody? No, haven't used rhos. So, yep, we love Greek letters. There we go. It's a mass per unit length. Okay. So the m is mass, and the L would be the length. If a rod is not homogeneous, then we could define the mass as a function of the length. So because it's not going to be constant at different points, we can say because it changes, our mass could go up or down relative to what the length is. So we'd say our m is going to be a function that depends on how far we are from one end of our rod. So we just choose to define it from one end. We could pick left end, right end, some point in the middle. We're just going to pick the left end to make things simple for us. So depending on how long this x is, my mass will vary. So we're expecting it to increase as we go from left to right. And so we're saying that it is some function that depends on x. That's why we're saying m is equal to f of x. So far, so good? All right. Now, suppose we're looking between 2 points, so somewhere in the middle of our rod. So then we would call that mass in that section kind of the change in mass, or a delta M. So this would be our delta M in this section here that you can see in the diagram. And that's where my left end is x1 units away, and my right end of that section is x2 units away from the left end of my whole rod. Alien. The second rod? Yeah, so we're interested in the mass of this little red section. So we call it delta M because we're saying from the left end, let's see, from the left end up to there, that's going to be mass 1. And from the left end up to there, that's going to be mass 2. If we subtract those two, we'll get the mass of the red section. And we're just calling it delta M because that's the difference between these two masses. Or it's the change in mass between M1 and M2. We can't take a fraction because we're assuming that every little section of this size isn't necessarily the same mass. So that's what we mean when we say that this is not homogeneous. So the mass is different in different sections of the rod. So suppose I had this little red section to be over there. This mass is actually different than the same length over here because our rod isn't uniform in its density. Some parts are more dense, some parts are less dense. So if I tried to balance it by holding it up on my finger right in the middle point, it wouldn't balance because the density is not the same on both sides. It changes as we go through the rod. So there are sections of the rod that are heavier than other sections of the same size. Yeah, in fact, it almost always happens in real life because of impurities in whatever our rod is made of. To some degree it happens. Now, the more pure it is, the more balanced and the more uniform something will be. But once we get down to really precise measurements, nothing really in real life will be uniform density. Now, here I talked about M1 and M2. Because these are functions of x, rather than using M for mass, we could say that this first section is f of x1. So that's the mass of that first section. And then the second section, up to there, that is f of x2. So that's why when we're looking for what's the mass of this section, we're doing f of x2 minus f of x1. We're finding the difference in those two masses to find out what's the mass of that little red section. We're finding an average density. So this rho is density, and it's an average density because I'm looking at the change in mass over the change in length, which means I'm looking at what's the mass of that red section over whatever this length is here. That's my, I should say, delta x, which is in the denominator. Because I'm interested in density, not just what the mass is. My numerator is mass, but if I do mass per length, then I'm getting a linear density. Mass per volume is probably a density that you're more familiar with. So how much mass is there in this volume of stuff? But when we have a rod, then we talk about linear density. as in for this length, what's the mass of that section? When we do the ratio, it gives me the density or average density of that section. Yes? Yep. Yeah, so f of x2 minus f of x1, that's just telling us what's the mass of that little red section. Well, x2 minus x1 gives me this blue delta x here. Gives me just the length of that section. And so what it's giving me is a mass per length. And if I just do that mass over the length of that section, that's giving me the average density of that red piece. Okay? So understanding this is the hardest part of this section. Doing the math is simple. Understanding what's going on is what will challenge our brains. Question? Yeah, so we'll be given some function that models how the mass changes as we go from one end to the other end. And in real life, the way they would get that is they would do some test sections to find out what's the mass in this section, mass over there, get a bunch of data points, do a regression to come up with a model that shows how it changes as you go from left to right. Italian. Yep. Grams over centimeters, something like that would be the units. So units of mass over units of length. Yep. That's what linear density is. Density, as most people understand it, is going to be a unit volume over volume per, what would it be? My brain is failing me at the moment. Could be volume per one of the measurements, so volume per length kind of thing could be a density. Yeah, so it would be cubic something, which is volume, over whatever we're comparing it to. Awesome. Do you have a question? Yep. 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 Well, this is a slope equation, right? So I'm doing change in y over change in x, right? So they're not the same values necessarily. So if we get the idea down, then if we're looking for the linear density, that's considered the instantaneous density at some point in the line. So we're going to do the limit as x2 approaches x1. So as this delta x gets smaller and smaller and becomes infinitely narrow, we can say, what's the density at that point in our rod? So we're doing the limit, but if we just do the limit as delta x goes to 0 of delta m over delta x, that's a derivative, right? So that is just dm dx, which is f prime of x. Yes? That would give us the average density over the whole thing, but our goal at this point was to just get us set up for doing what is the density at this point. And that's what this down here is doing. It's saying at this point in the rod, what is the density there? And we call that the linear density, which means it's kind of like an instantaneous, but it's not with respect to time, it's with respect to length. And it's at that infinitely thin segment, how dense is the rod? No, infinitely thin. Uh-huh. Well, there, your mass is going to 0, right? Which is your numerator. But your length is also going to 0, your change in x, because this thickness is the delta x. It's infinitely thin, which means it's going to 0. So going to 0, so this delta x is going to 0 down here, which is what a limit is doing. So at this infinitely thin point, what is the change in mass over change in length? Which again is hard for us to picture, but if you think velocity, at an instant in time, at that instant, you could say, well, it's kind of not moving. How can you measure how fast it's going? But it makes intuitive sense because at an instant in time, we can understand that you can actually be moving. Here, it's the same idea. At this infinitely thin point, what would the density of the rod be? How would the mass compare to the length when both of them are going to 0? Again, it's understanding the ideas that are the hardest part. The math is going to be simple. Yep. Mm-hmm. We can choose it from wherever we want. And so what's going to happen is our function, our mass function, will be defined from one end or the other end. And to simplify it, we'll typically just do the left end. But we could adjust it however we needed to. So here's what a question would look like. And then you'll say, wow, that was easy. How come we went through all that other stuff? Just because we were trying to understand what's going on. So here's the easy part. If I want to find the average density in the rod between 3 meters and 3.6 meters, then I'm going to do change in mass over change in length. My change in mass will be f of 3.6 minus f of 3. At the top of the page, we're given a function, which will represent our mass. And it's all over the change in x, which is 6.3 minus 3. Which is not too difficult. Okay, questions with number 2? Nope. Number 3, we want the linear density, which is the derivative of our function, and then plug in the value. So the derivative is just 1/2 times x. So I brought the 2 down from the, we had again, 1/4 x squared. Bring the 2 down, which turns into a half. Subtract 1, and then we'll just plug in the x value of 3, which is saying 3 meters from the left end, at that infinitely thin sliver, the mass per length at that point is 1.5 kilograms per meter. Yes. Yeah, at 3, it's 1.5 kilograms per meter. Well, we plug in a different number. Suppose I plugged in at 4 meters. Then my linear density at 4 meters, if I came up here to 4 meters, and if I plugged it in, then I would get a linear density of 2 kilograms per meter. So as I go from left to right, it looks like my density is increasing. So it gets heavier the further we go to the right. Yes? Because the first part was looking for an average. So we're looking at this section of the rod. What's the average density through this whole section? Whereas in the second one, we're looking at this one point, this infinitely thin sliver, what's the density at that point? It's not average because it's at an instant, because it's infinitely thin. Okay? Anybody need a minute to talk to your neighbor to clear things up? I don't know if I believe you. Okay, fine. Take a minute, chat with your neighbor, get questions answered. Okay, next question. So this time we're going to do a population situation. So number of items in a population, the average growth rate is how does the population change, that's delta n, over some time interval delta t. And if we can model our population with some function, then we have f of t representing how or what the population is relative to time. Yes? We would wait till chapter 8. So the question was, for people online, if it was a logarithmic function, what would we do? And yep, we wait till chapter 8. Logarithmic are more realistic for many populations. Yep. Yep. Yes. Yeah, we'll put everything together because it's exciting. Okay. Instantaneous rate of growth will be just the limit as T2 approaches T1, or as that time interval goes to 0, how does the change in population over change in time change? Or what does that look like? And again, that's a derivative of the population with respect to time. A little bit easier than that linear density idea. So a little more intuitive. Yes, Alian? N is population. So number of items in a population at a time t is n, which is equal to some function of time. Oh, nothing. Just hanging out. Question number 4. Population in a bacteria culture is given by this function. We want to find the growth rate after 4 hours. What do? Find the derivative and plug in 4. There you go. The math is easy. So there's my derivative function. So that'll tell me how the population is changing at any instant in time, and then I can pick whatever instant in time I'm interested in, which in this case is 4. Well, it's bacteria, and we're given time is in hours, so it's the number of bacteria per hour. Yeah, depending on kind of the situation, there'll be different units. Yep, that notation is good. And we could just keep doing different applications. So every question is different. So I just refer you to a chemistry example in the textbook, and then just do a bunch of practice so that you see the variety of types of questions where we could apply these ideas, where we take the derivative of some function and then plug in a number that tells us how is that thing changing at some instant. There we go. The end of 3.3.